guys, welcome to this science paper only presentation. So the first question reads, a student measures the diameter of some identical steel balls. So whenever they use the term identical, this means these balls are of the same size and they have the same diameter. Okay, figure 1.1 shows the arrangement she uses. Now as you can see here, we are using the ruler to measure the length of these balls starting from point A up to point B. So whenever you are measuring something using a meter rule or a measuring tape, you need to start from 0. So now as you can see here, we are not starting from 0. We are starting at this point here, which we can say approximately this one is going to be 1.5, ending at B, where we are going to have 5.8 approximately. Now the first question, which is question A, Roman number 1 is saying, using the ruler in figure 1.1, determine the distance AB on figure 1.1. So to determine the distance here, what we are going to do, we are going to say 5.8 minus 1.5. Why are we doing like this? We want our measurement to start from 0. So whenever you are measuring something, always you need to start from 0. Okay, so when I say 5.8 minus 1.5, I'm going to get 4.3. So 4.3 centimeters is our answer here. Let's see the next question. Next question, which is Roman number 2. It is saying, use the distance AB to determine the diameter of one steel ball. So the total length of AB was 4.3. And let me just check how many steel balls do we have here. So they are about 1, 2, 3, 4, 5, 6, 7, 8. So they are about 8. So for us to know the diameter of each steel ball, we are going to divide this length here by 8. Then when I divide, I'm just going to get 0.5 approximately. So if you want, you can just say 0.5 or 0.54. So I'm just going to say 0.54 approximately. Then as for B, the mass of some steel ball is 54 grams and the total volume of these steel balls is 6.9 centimeters cubed. Calculate the density of the steel. So density is equal to mass over volume. So the mass that we have here, it is 54 grams divided by the volume that we have, which is 6.9 centimeters cubic. Then when I divide here, I'm going to get 7.8 approximately. So at the end here, they have included the units for us. So there is no need for us to include the units. Let's see the next question. So the next question is coming from travel graph, and it is saying figure 2.1 shows a speed time graph for a cyclist. So we have the points starting from point S up to point Z. So now let me just try to interpolate what is happening starting from point S up to point Z. So from point S up to point T, here we can say the cyclist was moving with constant speed. So whenever you have a line straight like this, the speed where it is not changing but the time is changing, that one is going to indicate the constant speed. Apart from that one, we have T up to W. T up to W, this one is indicating the constant acceleration or uniformly acceleration, meaning from T up to W, the cyclist was accelerating because the speed is changing and also the time is changing. Similarly, from W up to X here, since this one here is same as this one here, meaning for S and T and also W and X, they are just the same, meaning from W up to X, the cyclist was moving with constant speed. Then let's try to look at X and Y. What was happening here? from x up to y. Here there was constant deceleration. When you say constant deceleration, meaning the cyclist was reducing in speed up to x, up to y. Then from y up to z, here we can just say the cyclist was not moving. Why are we saying the cyclist was not moving? As you can see here, it is just time which is changing. Let me not forget, in the x-axis here we have time, then in the y-axis here we have the speed. So when you consider these two things, you are going to find that from y up to z, the cyclist was not even moving because the time is only which is changing here. Let's try to answer the questions. So question A reads, in figure 2.1, the sections ST, TW, WX, XY, and YZ indicate stages of the cyclist's journey. State one section which shows the cyclist moving with Roman numeral number 1, constant speed. So let's try to check out here. Where was the cyclist moving with constant speed? So here we can just choose S and T, or we can just choose W and X. Then as for Roman numeral number 2, constant deceleration. Where are we having constant deceleration? It is from X up to Y. So we can say X, Y. Then as for Roman numeral number 3, constant non-zero acceleration. Constant non-zero acceleration. So you need to understand here, they are not saying zero acceleration, but they are saying constant acceleration or non-zero acceleration. So meaning here, we can just say T and W. Now, let me not forget, when an object is moving with constant speed, it is going to have zero acceleration, meaning from S up to T, there was no acceleration here. You are going to have zero acceleration and constant speed. Even at W and X, here you are going to have constant speed but zero acceleration. So we can just say the answer here is just going to be TW. Then as for question B, it is saying, calculate the distance traveled by the cyclist in section ST. Now, to calculate this one here, let's try to look at the shape of ST. The shape of ST is this one here. So let me just draw it again. We have this one. Yeah. So this one you can just say it is the rectangle. Now the area of the rectangle, or the area under the graph, is equal to the distance traveled by an object. So since this one is a rectangle, we can just say the area of the rectangle is going to be equal to L multiplied by width, which is length multiplied by width. So area is going to be equal to, what is our length that we have here? So the length that we have here, we can just say is going to be 8, okay, which is this one here. Then multiplied by the width that we have. So the width here, approximately, I'm going to say 13. So we have 13. Where is this 13 coming from? Let me just show you. At this point here, we are having 10. So if you just count from 10 up to 20, here we have 10 small boxes. So where we are having T here at this point here, that is when we are having 13. So when we multiply, the area is going to be equal to, so here we are going to have 104. So now this 104 is same as the distance traveled by an object from S up to T. So here we are just going to say this one. So here we can just say the answer is going to be 104. Don't forget here they have included the units for us, which are meters. So do not include them. Let's see the next question. So the next question is, figure 3.1 shows a metal block and its dimensions. So we have this 2.0 centimeters, which is the width, 12.0 centimeters, which is the length, and 3.0 centimeters, which is the height. The first question, which is Roman numeral number 1, is saying, calculate the area of the metal block in contact with the ground. So the first thing here, we need to identify the formula that we are supposed to use at this point here. So I'm going to say area is going to be equal to L multiplied by breadth, which is length multiplied by breadth multiplied by the height. So the length that we have here is just 12, multiplied by the breadth, which is 2, multiplied by the height, which is 3. Then when I multiply here, I'm going to get 72. So centimeters squared, which is for the area. So they have included the units for us even at this point. Let's see the next question. The next question is, the mass of the metal block is 0.84 kgs. Calculate the weight of the metal block. So by using this formula, where we are going to say weight is equal to mass multiplied by gravity, you can easily calculate the weight of an object. So here we are going to say weight we don't have. Mass we have, which is 0.84 kgs. Then multiply by the acceleration due to gravity, which is approximately 10 meters per second squared. But in some cases, you can take 9.8. So when I multiply here, I'm going to get 8.4 newtons. So even here, they have included the units for us. But sometimes in an exam, they're not going to include the units for you. You need to remember them. That's very, very important. Question B leads. A different metal block has a weight of 24 newtons. The area of this metal block in contact with the ground is 4.0 centimeters squared. Calculate the pressure of this block on the ground. So by using this formula, where we are going to say pressure is going to be equal to force divided by the area, we can easily calculate the pressure in contact with the ground. Now we have 3 marks here, meaning this area which they have given us, we need to convert it from the centimeters squared to meters squared. Okay, so I'm going to say 1 meter squared is equivalent to 10,000 centimeters squared. Now since we want to convert 4 centimeters squared into meters squared, we are going to say 4 centimeters squared multiplied by 1 meter squared divided by 10,000 centimeters squared. So centimeters squared and centimeters squared, they are going to cancel each other. Then when I multiply 4 multiplied by 1 meter squared, I'm going to get 4 meters squared divided by 10,000. I'm going to get 0.0004 centimeters squared. So this one is our area that we are going to use to calculate now the pressure. So here we have been given the force, which is 24 newtons, divided by the area, which I've already converted from centimeters squared to meters squared, which is 0.0004 meters squared. So when I divide here, I'm going to get 60,000 here. So remember here they haven't included the units for us, meaning we need to include them. So the units we are just going to say they are newtons per meter squared. So this one is our final answer. Let's try to look at the next question. So the next question is coming from rectilinear propagation of light. And it is saying, a ray of light in glass is incident on a boundary with air. State what happens to the ray when the angle of incidence of the ray is Roman numeral number 1 less than the critical angle of the glass. So whenever the incident ray is less than the critical angle, you're going to find that the ray is going to bend away from the normal. So here we can just say bending away from the normal. Then as for Roman numeral number 2, it is saying when the incident ray is greater than the critical angle of the glass. So whenever the incident ray is greater than the critical angle, the total internal reflection is going to occur. So meaning here we're just going to say total internal reflection will occur. It's very, very important. You need to remember it. So whenever the angle of incidence is greater than the critical angle, you're going to find that the total internal reflection is going to occur. And this one here is one of the conditions necessary for total internal reflection to occur. So in an exam, if they ask you, write one condition necessary for total internal reflection to occur, you are going to say the angle of incidence should be greater than the critical angle. That's very, very important. Let's see the next question. So the next question, which is question B, reads, figure 6.1 shows a ray of light incident on a glass block at A. The critical angle of the glass is 41 degrees. So we have 41 degrees as the critical angle. So we can say critical angle, which is C, is equal to 41 degrees. Now as for Roman numeral number 1, it is saying on figure 6.1, without calculation, continue the ray from point B until it leaves the glass block 2 marks. So here, as I'm from reading question A, we can easily identify that here maybe total internal reflection was occurring here. So I'm just going to draw the ray which is going to show the total internal reflection of light. Okay, so I'm going to start from point B until the ray leaves the glass block. Let me just imagine at this point here. Now you need also to draw the normal ray. So let me just draw it approximately like this. So it's going to be our normal ray. Now whenever the ray is coming from high dense medium, which is the glass block, going to the less dense medium, it bends away from the normal. So here we need to make sure that the ray bends away from the normal. So what are we going to do here? So we need to indicate that it is bending away from the normal, like this. So that is how we are going to draw this one here. Now as for Roman numeral number 2, it is saying calculate the refractive index of the glass. We need to calculate the refractive index of the glass. We have been given the critical angle, so you can just easily use this formula where we're going to say sin critical is equal to 1 over refractive index. Therefore, we can just say refractive index is going to be equal to 1 divided by sin critical. When you make the refractive index the subject of the formula, you need to have something like this one here. So here just mean you multiply here. Okay. So I'm going to say refractive index is going to be equal to 1 divided by the sin critical. So in this case here, sin critical, it is just 41 degrees. Then refractive index is just going to be equal to, so here you need to say 1 divided by, so when I punch on the calculator sin 41, I'm going to have 0.656. Then when I divide here, I'm going to get the refractive index, which is going to be 1.5. In most of the cases, the refractive index of the glass, it is just 1.5. So I'm just going to say, so here our final answer is just going to be 1.5. So refractive index, do not include the units. Do not include the units because it is a ratio. Let's see the next question. The next question reads, a loudspeaker produces a sound wave of constant frequency. Question A. State what is meant by frequency. So what is frequency? So frequency is defined as the number of waves produced in 1 second. The number of waves produced in 1 second. Then as for question B, the sound wave travels in air towards a barrier with a small gap at its center. Figure 7.1 represents the complexions of the wave traveling towards the barrier. So we have the direction of travel like this. Okay. Then here we have the wavelength, which is being represented by the lambda. So whenever you see this symbol here, this one is called the lambda. Okay, so here we have the barriers. Now, as for question Roman number 1, it is saying, state what is made by a complexion. What is complexion? So complexion is just defined as the process by which particles of a wave are brought together. That is to compress. Whenever you bring something together, that is complexion. Now specifically, when you bring the particles of a wave together, that is called complexion. Then as for Roman number 2, it is saying the width of the gap is smaller than the wavelength, which is the lambda of the wave. On figure 7.1, draw the pattern of the complexion after the sound wave has passed through the gap. So let's see. This one here is the gap. So whenever the wave passes through the gap, or let me just say, as you can see, the way the wave is moving like this here, once it passes through this gap here, you're going to find that it is going to undergo diffraction. When you talk of diffraction, meaning it is going to change the pattern, the way the wave is moving, the pattern is going to change. So in this case here, once this wave passes through this point here, you're going to find that they are going to move in this way. So this one is called diffraction. That is how these waves are going to move, or the particles. So this is how you are supposed to draw like this. That's all. Let's see the next one. So as for Roman number 3, it is saying the barrier is adjusted so that the gap become wider. Okay. Then the question reads, describe how this affects the pattern of the complexions after the sound wave has passed through the gap. So here we are going to say the sound wave will undergo diffraction, thereby changing the pattern of the complexion. That's the answer. Let's see the next one. So the next one is coming from transformer, and it reads, a device in figure 8.1 is connected to a 240 volts mains supply. The device produces a potential difference PD of 12 volts between A and B. A 12 volts lamp is connected between A and B. So, usually the transformer has two sides. It has what we call the primary core and also the secondary core. Usually the primary core is called the input side, where the voltage is being inputted. Then when it comes to the secondary core, this one is the output. Okay, so let me just try to collect the data on the thing that we have been given here. So as for voltage on the primary coil, we just represent it by using Vp to represent the primary coil. So here we have 240 volts. Then as for the number of turns, I'm going to say capital letter N and P. The number of turns on the primary coil, which is 8,000. Then the voltage on the secondary coil, we say Vs, which is 12 volts. What about the number of turns on the secondary coil? Here we don't have. So let's see the question. So as for the first one, which is Roman number 1, it is saying calculate the number of turns on the secondary coil. Use information from figure 8.1. So whenever you have been told to find the number of turns on the secondary coil or on the primary coil, or whether the voltage, you need to use this formula here, where you're going to say the voltage on the primary coil divided by the voltage on the secondary coil is equal to the number of turns on the primary coil divided by the number of turns on the secondary coil. So if here we multiply, what are we going to have? We are going to have the voltage on the primary coil multiplied by the number of turns on the secondary coil being equal to the voltage on the secondary coil multiplied by the number of turns on the primary coil. So you can use you can just use this one here, or use this one here, whichever way you choose. So now I'm going to use this one here. So here we have been told to calculate the number of turns on the secondary coil, which is NS. Okay. So now, according to the data that we have collected here, I'm going to say the voltage on the primary coil if I use this formula here. So the voltage on the primary coil, which is 240 volts, multiplied by the number of turns on the secondary coil, which we don't have, being equal to the voltage on the secondary coil, which is 12 volts, multiplied by the number of turns on the primary coil, which is 8,000 turns. Multiply here 12 volts multiplied by 80,000 turns, I'm going to get 96,000. Then here, when I multiply 240 volts multiplied by the number of turns on the secondary coil, I'm going to get 240 volts number of turns on the secondary coil. Then here, when I divide by 240 volts, even here by 240 volts, what am I going to get? So we can say the number of turns on the secondary coil is going to be equal to, okay, so we have 96,000 volts divided by 240 volts. I'm going to get 400. So this 400, they are just the number of turns on the secondary coil. So this one is our answer. So let me just write it here. So here we have 400 turns. Then as for Roman number 2, it is saying, state the name of the device shown in figure 8.1. Of course, we know that this one is a transformer. We know that this one is a transformer. Now, what kind of a transformer is this one? So if we say these number of turns here are for the secondary, where we are going to say here we have 400 number of turns. Then here we have 8,000. So usually we have two types of transformers. We have the step-down transformer and the step-up transformer. So whenever you have more number of turns on the primary coil, so whenever you have the number of turns, whenever you have more number of turns on the primary coil, like this one here, we have 8,000 number of turns on the primary coil, and less number of turns on the secondary coil. This one is going to be the step-down transformer. Then when you have less number of turns on the primary coil, suppose you have 40 here, and then here you have 400, meaning this one is going to be the step-up transformer. Okay, so the answer here is just going to be step-down transformer. Then as for Roman number 3, it is saying the device includes two cores. State the material used for the cores. So usually they use the soft iron cores. So I'm just going to say soft iron cores. Let's see the next question. So the next question is coming from the radioactivity, and it reads, Table 12.1 gives some properties of 3 different types of radiation. We have the type of radiation, nature, relative charge, and also ionizing ability. So let me start with the type of radiation. So we have gamma here. The nature of gamma, it is just electromagnetic wave. Then in terms of the relative charge, in this part here, it is just going to have 0. Then ionizing ability, it is just wrong. So in talk of ionizing ability, specifically ionization, this one is the ability of a metal or a non-metal to form an ion or a cation. So let's come to beta or beta, this one, the nature of beta. So the nature of beta, it is to that of an electron. So we can say an electron. Then in terms of the relative charge, it has -1. Then ionizing ability, medium. Then the last one, alpha, Alpha, it has a nature to that of helium. So helium looks something like this, where it is going to have the mass number of 4, and then the proton number of 2. Okay. So when it comes to the relative charge, here we are going to say positive 2 or plus 2. Then it comes to ionizing ability. Ionizing ability, we are going to say higher or highest. Number 1, it is saying complete table 12.1 by writing the missing property in each of the empty boxes. Remarks. So we have already completed here. Now, where is this 2 coming from? So whenever an isotope undergoes alpha decay, you're going to find that the proton number is going to be reduced by what? By 2. Even the mass number is going to be reduced by what? By 4, not 2. The mass number of helium, it is 4. The proton number or electron number, it's 2. So whenever an isotope undergoes alpha decay, the proton number or the electron number is going to be reduced by 2, the mass number by 4. Okay. Then as for Roman number 2, it is saying state which type of radiation, alpha, beta, or gamma, is the most penetrating. So when it comes to this one here, let me just try to draw this. Usually this question even came in 2023 for internal ECZ candidates. They brought this one for the penetration. So here as for the alpha radiation, it can be stopped by a sheet of paper. Then when it comes to the gamma radiation can be stopped by a sheet of aluminium. Then as for the beta radiation, this one can be stopped by a sheet of lead. So the first one I'm saying, this one here, which I'm going to draw in a green color, it is representing the alpha, which can be stopped by a sheet of paper or plastic. Then the next one, which I'm going to draw in a blue color, this one here is representing the penetration of beta. So beta can be stopped by a sheet of aluminium. Then the last one, which I'm going to draw in a black color, this one is going to represent the penetration of the gamma or Y rays. So Y rays can be stopped by a sheet of lead. In short, gamma rays, they have highest penetration or most penetrating. They are most penetrating. So we can just say gamma. Then the next question, which is B. An isotope of beryllium, Be, has the nuclide notation, where we're going to have the mass number of 9, the proton number or electron number of 4. Figure 12.1 shows a diagram of one atom of this isotope. So this one here is showing the electrons. So how many electrons we have here? We have about 4 electrons. Now, since electrons are equal to the number of protons, so even the protons are going to be 4. So protons here we have 4. Electrons here we have 4. Electrons are equal to the number of protons. The question leads, complete the labeling of figure 12.1. State the names for X and for Y. So what is X? This one here. So there are how many? X is about 4. So meaning X is going to represent the protons. Why are we saying protons? Because the number of electrons are equal to the number of protons. So X is protons. Then Y is going to represent the neutrons. The next question. So the next question is coming from electricity. And the question reads, a student makes a 2.0 volts battery by connecting 2 cells of electromotive force, EMF, 2.0 volts in parallel. A battery, an ammeter with different ranges, and 3 different resistors are used to set up the circuit shown in figure 11.1. So we have 3 resistors, 2 resistors connected in parallel, which are these 2, and 1 connected in series, and also 2 batteries connected in parallel. That is one thing that you need to know here. So let's see the question. So as for the first one, which is question A, Roman numeral number 1, it is saying, explain what is meant by electromotive force. So in talk of electromotive force, it is same as PD, which is potential difference. So I'm going to say EMF is equal to energy divided by charge. Divided by charge. I'm going to say electromotive force is the energy produced in a conductor per coulomb. The energy produced in a conductor per coulomb. That is the definition for electromotive force. And then as for Roman numeral number 2, it is saying, state one advantage of using two cells in parallel rather than using a single 2.0 volts cell. So let's see. Suppose we are just using this one here. Forget about this one here. If we're just using this one here, then I decide to cut here. Is this circuit going to be a complete one? No. Now it will be an advantage of us using these two cells connected in parallel. Suppose I cut here. What is going to happen to the circuit? Nothing is going to happen to the circuit because we have also the extra one here. Okay. So in short here, they're just asking you the importance of us using these two resistors instead of just using one. So I'm just going to say, when one battery is affected, the other one won't be affected. Let's see the next one. Question B reads, resistor X and the 3.0 ohms resistor have a combined resistance that is equal to 2.0 ohms. Calculate the total resistance of the circuit. So when we combine X and 3.0 ohms, we are going to get this one here. Now let's just see where X and 3.0 ohms are coming from. So we have 3.0 ohms and also X. Once we combine them here, we are going to get what? 2.0 ohms. Now they are asking us the total resistance of the circuit, meaning the whole circuit. What is the resistance? Now mind you, once you find the resistance of these two here, which is this one here, now they have given us, meaning we need to also to add with one resistor here which is connected in series. So we're just going to say this 2.0 resistance, which is 2.0 ohms, plus this 2.0 ohms of these two here. So we can say, so here we can say 2 ohms plus 2 ohms. Then we are going to get 4 ohms. This 4 ohms is the total resistance of all of them, including those two connected in parallel and also the one connected in series. Then as for Roman numeral number 2, it is saying the resistance of X. So now we know that, let me just bring you back here. It is asking us to calculate the resistance of X. Now previously the question was saying the total resistance of these two here, it is just 2.0 ohms. So whenever you have been given two resistors connected in parallel, you can use this formula where you're going to say resistance is going to be equal to resistor 1 multiplied by resistor 2 divided by resistor 1 plus resistor 2. This one here only applies to two resistors connected in parallel. If there are three, you're not going to use this one here. You can use this one. So you can use this one here and so on. And now I'm going to use this one here for us to calculate X. So here I'm going to say X is going to represent resistor 1. Then 3.0 ohms is going to represent resistor 2. So here we can say total resistance that we have here is going to be 2, which is this one here. This 2 is coming from this question here, which is question B. They were saying resistor X and the 3.0 ohms resistors have a combined resistor that is equal to 0.2 ohms. So that is where I'm getting 2.0 ohms. So here I'm just going to set 2 ohms being equal to resistor 1, which is X multiplied by resistor 2, which is 3 ohms, divided by resistor 1, which is X, plus resistor 2, which is 3. So when I multiply here, I'm going to get 2X plus 6 ohms being equal to 3X. So since these two, they are like terms, meaning this 2X is going to cross an equal sign. Then I'm going to remain with 6 ohms here being equal to 3X minus 2X. Now, 3X minus 2X, I'm going to get X. So X is going to be equal to 6 ohms. So meaning the value of X here is just going to be 6 ohms. We can do that by saying we have 2 being equal to ohms. This one is our answer. Let's see the last one. So the last one is saying determine the reading of the ammeter, meaning they are asking us to calculate the current. So current is equal to voltage divided by the resistance. So now the voltage that we have here, let me just see it. So we have this one here and also this one here. So when we add these two, we are going to get what? 4. So we can say 4 volts divided by the total resistance. So the total resistance was what? 4 ohms. Then when I divide here, I'm going to get 1 amp. So meaning our final answer here is just going to be 1 amp. Usually current is measured in amps. So that was the last one. If you're new to this channel, share this video to your friends. Peace.